Hello there. In this lesson, we're going to look at energy and physical changes. And so in this little cup here, you can see that this little Lego guy, he's made of gallium and just poured a little bit of hot water on top of it. And you can see that the gallium is melting and turning into this little puddle down here. And that's due to energy being transferred from the water that's in the surroundings into this metal and causing it to change state. So that's what we're going to look at today is physical changes, like changes of state that are related to energy in the surroundings. Any chemical component that's under study, we're going to call the system, and anything that energy can be added or removed from into or out of the system, we're going to call the surroundings. And so surroundings could be anything, anywhere, anything that has in contact with the system itself, which means it could be the whole universe ultimately. So physical changes we're going to look at are things like changes in state, right? And also dissolving molecules. So three different systems that we're going to look at. One's called an open system, and this is where energy and matter can both be exchanged with the surroundings. That would be this example here. If you put something in this cup, heat can go in and out. Also matter, if it like boils or something, could fly away. There's nothing keeping it there. The second one's called a closed system. Only energy can be exchanged with the surroundings. Everything else has to stay in there. So that'd be this guy. Closed. This is open. If something evaporates, it's going to stay in the jar, but still energy can go in and out through the sides of the glass here. Isolated system is where you keep the energy from being transferred here. So this is close to isolated system. We have some insulating matter going around the jar here. That will reduce the amount of energy that goes in and out. It's not actually possible to completely stop energy from getting through these substances, but we can minimize it. And some of our systems that we study, we're going to use something like this in order to quantify the energy that's moving in and out. Okay, some more terminology that we're going to use throughout this unit. The first one being enthalpy. So enthalpy is referring to the amount of internal energy that a substance has. It's all the particle motion and the potential energy and everything else that goes into a substance, all forms of energy. So it's not really possible to measure a substance's enthalpy as it is, but we can measure changes in enthalpy because energy can't be created or destroyed, and it has to be either transferred into or out of the system for any type of change. So if we have something like a positive enthalpy change in enthalpy. So this would be an enthalpy of water, this would be an enthalpy of ice. In order to go from ice to water, there has to be a positive enthalpy change to increase the amount of internal energy. And then to go from water to ice, there's got to be a negative enthalpy change because you're going to release energy to do that. So the energy that's lost has to go somewhere, right? And we can measure that. We can always measure the change in temperature in the surroundings. And if we know the heat capacity and the mass, we can work out the amount of energy that got transferred. So that's your heat. Heat is the energy being transferred. So we can monitor the surroundings, figure out how much heat was transferred, and then by deduction determine that the enthalpy either increased or decreased by looking at the surroundings. This all works only if we keep things at constant pressure, which is what we're going to do throughout this course. So a neat thing happens as substances warm and change state. We'll use ice as an example. If you have frozen water or ice, like an ice cube, and you put it into a drink, it will warm up the ice until it gets to 0 degrees. At 0 degrees, then it'll start to melt, and it'll all stay at 0 degrees until that's complete. Now that doesn't mean that energy isn't going in there, it's just not going into raising the temperature. It's going into breaking bonds between those particles and turning it into water. Once you have water, it's all water, well then it can start to heat up again, and you'll see the temperature change until you get to 100 degrees Celsius, right? And then the same thing happens. The temperature stops rising and you get boiling occurring until all of the water is turned to steam. And then that steam can continue to rise after that. So if you're going to be burned with something, take water over steam, because steam or vapor can be a lot hotter. So the energy required for those state changes can be quantified. For melting and freezing, it's called the enthalpy of fusion. And so that's the amount of energy needed per gram of the substance in order to either turn it into a solid or turn it into a liquid, depending on whether you're adding or removing that amount of energy. It's given a little symbol, delta H, with the FUS for fusion. And then we also have the similar thing happening when you get to the boiling point. And this is the energy of vaporization, or enthalpy of vaporization, sometimes called latent heat of vaporization. And similar symbol, just a VAP, and same deal, same amount of energy needed for every gram of, if it's water, to change it from a liquid to a gas, or from a gas to a liquid if you are removing that energy. Okay, so when you have a change happening, I find it helpful to divide the change into two phases. You got the system and you got the surroundings. This one's asking if you have 10 grams of ice, system is the ice, and it melts and causes the surroundings 250 grams of water, 250 grams of water, to cool down from 15 degrees to 9 degrees. So we want to know the amount of heat energy that went into the system, and we're going to work that out with Q equals mc delta T of the surroundings. So the energy that the surroundings lost was, we have 250 grams. We know that the heat capacity of water is 4.18 joules per gram per degree Celsius. And we know that the temperature change was from 15 to 9 degrees, so that's -6 degrees Celsius. So if we work that out, let's do it here, 250 times 4.18 times -6, and you get -6270 joules. Since the system is absorbing that energy, the delta H, the enthalpy change, is going to be the opposite symbol, the opposite sign of the heat change. So if the heat that left the surroundings is going to be absorbed by the system, it'll be the same amount but opposite sign. So delta H is going to equal positive 6,270 joules, or 6.27 kilojoules. And then we wanted it per mole, so we need to divide that by the number of moles. So we got 10 grams here. Let's change that 10 grams into moles. 10.0 grams. It's water, so it's 18 grams per mole. And that equals 10 divided by 18. 10 divided by 18 equals 0.56 moles. So we'll divide it, 0.56 moles. And so our molar enthalpy of fusion here is 6.27 divided by 0.56 equals, and I've got 11.2 kilojoules per mole. All right, in this example, what we have is energy being removed from water and some of it turning into ice. And so we have a chance here to distinguish between two enthalpy values. So here is some, like an enthalpy change that's occurring that is producing ice. So this is a delta H. And then here we have this standard value, which is also delta H per gram. So the standard thing here with the little degree sign, that represents under like standard conditions like the states that everything would be under standard temperature and pressure. But I'm going to use that to help us to distinguish between enthalpies that could be for any amount and enthalpies that are for a set amount, like 1 gram. So there's a relationship between these, of course. The enthalpy, the whole enthalpy of the change that's going on in whatever reaction you're looking at is going to be whatever mass it is times the enthalpy, the standard enthalpy for this water that's doing the change. So you get 2 enthalpy values there. One of them is the number of joules per gram, and this is the number of joules that is actually extracted from some water at 0 and causing it to freeze. So then if you want to figure out like the mass that you need, you can rearrange that. And you could say that the total enthalpy here is going to be divided by the standard enthalpy here, and then you'll end up with 8,500 joules divided by 330 joules per gram. And I'm kind of getting squished down here, but let's see what that works out to. So 8,500 divided by 330 equals, and we end up with 25.8 grams. So that's one way of looking at it. Some people like little formulas like that to help them remember and keep things straight. Myself, I always like to focus on the units that we're using here. And so I would tend to use a factor label method to solve this and not a formula. So you could do that just by saying, well, what are we looking for here? We're looking for a mass. What are we given? We're given 8,500 joules of enthalpy change. And then we can convert from the joules into the grams by using this conversion value, which is 330 joules for every 1 gram. And you see the joules cancel out, and you would end up with the same answer, 25.8 grams. So either way works. If you like little equations, no problem. I'm going to tend to use a factor label method, which is going to focus on the units. But either way, just to distinguish between enthalpies that are, for a specific amount, like per gram or a mole. Oftentimes it'll be a mole, especially when we get into chemical reactions, from ones that don't have that. Okay, just watch your units, and yeah, next. A challenge involving enthalpies of fusion or vaporization might be to include some warming as well as the state change. So if you recall our graph here, what happens is if we've got some water at 15 degrees Celsius, it's going to have to heat up first to get to 100, right? And then once it gets to 100, then it's going to have to vaporize. And so this, we could work out the energy required by using our Q equals MC delta T. And this, we could work out by using the enthalpy needed, which is like the mass times the standard enthalpy of vaporization. Right, so we have heating, and then we have boiling. So let's do the heating first. We got Q equals MC delta T. The mass of 500 milliliters of water is 500 grams, right? 1 gram per milliliter is the density of water. 4.18 is the heat capacity of water, joules per gram per degree Celsius. And the temperature change, we got to go from 15 degrees Celsius all the way to 100. So that's going to be 85 degrees. And so the energy required for that is 500 times 4.18 times 85 equals, that's a big number. So we got 177,650 joules. Great. Now we've got water that's at the boiling point, and we want to change the state. So to boil, we're going to want to know the enthalpy change needed. And so what we're going to do is use our standard enthalpy of vaporization and multiply by the mass. So in the form of an equation, you could say it's mass times the standard enthalpy of vaporization. Again, it's 500 grams, and the standard enthalpy of vaporization is 2,300 joules per gram. All right, so we can multiply that. 500 times 2,300 equals, whoa, even bigger number. So we got 1,150,000 joules. All right, so the total energy is just the sum of them. So total, oh, what happened there? Total equals, we're going to add the two together. So that's heat plus boil. So that's the 177,650 plus the 1,150,000 joules, and that comes out to plus 177,650 equals. So we got 1,327,650. And if we're doing this by sig figs, well, I guess we got 2.0 cups there. I guess it's going to be, we can change it to kilojoules, so that'd be 1,300 kilojoules if we're doing our sig figs. My pen's acting weird.